Hello. The title of my talk is Effective Enabling for Intel Deep Link Technology. My name is Max D'Amica, and I'm a principal engineer at Intel. I've been with Intel for 25 years. I'm based in Oregon. I've worked in all areas of software development during my time and currently on a commercial and collaborative solutions team within Intel. Today I'm going to talk to you about Intel Deep Link technology and how you as a software developer can enable for Intel Deep Link technology is the intelligent harnessing of Intel CPUs and GPUs to improve the performance of content creation, gaming, commercial, and productivity applications. I'll cover the process, tools, and fundamentals for effective enabling of your application. And then I'll follow with case studies that highlight different aspects of employing Intel Deep Link technology. The agenda for today is as follows. First, we'll go over Intel Deep Link technology and the development strategies used to employ it. Second, we'll go over 7 enabling fundamentals. So these are the basics on helping you as a developer understand how to employ it, how to use it, and some common issues that you may have to address when you're enabling the technology. And then last, we'll go over 3 different case studies that highlight different aspects of enabling Intel Deep Link technology. So what is Intel Deep Link technology? It's a harnessing of the compute power that is comprised by 11th gen Intel Core processors, as well as the GPUs in those processors, Intel Iris Xe Max and Intel Iris Xe graphics. And then if you peel a layer down, what comprises it are the CPUs, of course, the GPUs, as well as special instructions for increasing the performance of AI applications, such as VNNI, DP4A, as well as media encoders. So each of the GPUs, the integrated and the discrete, have additional capabilities with respect to media encoding compared to previous generations of Intel processors. This is all accomplished under a common software framework so that you as a developer can have a fair amount of usage and reusage from the coding choices you make when you're developing for Intel Deep Link technology. And so when it comes to taking advantage of Intel Deep Link technology, the goal is to fit in your standard development process and development tools. Like many different performance optimization approaches, there are many ways to do it, but a good 4-step process is detailed on the right. So first, it starts with understanding your application, and then determining opportunities for parallelism to increase performance by taking advantage of the different accelerators. Once you determine where you want to take advantage of the different accelerators, that's the CPUs and the GPUs, then you can pursue one of 2 different approaches. It's either a library approach or a direct programming approach. And then lastly, you'll debug and optimize that. So some details between these 2 different approaches. The first one is taking advantage of a multi-device enabled libraries. And for that, Intel has 2 different ways that you can take advantage of it. One is if your application is media focused, then you can take advantage of the Media SDK, and there is a multi-device encoding plugin. The second is if you're doing inference and you're using OpenVINO, you can take advantage of the multi-device and heterogeneous plugin. So those are the 2 routes if you want to use a library where much of the work of taking advantage of Deep Link technology is done for you somewhat automatically. And that's what I call a library-based approach. And that contrasts against direct programming, where you would take advantage of an API or a library to have more direct involvement in separating the work, in handing out the work to the different accelerators and managing it. And the different techniques or different APIs for doing that are listed here, from OpenCL, DX12 meta commands to issue to the 2 GPUs, 1DNN, employing TBB, async node and resumable task, or employing data parallel C++ and device fission. The underlined techniques here are ones where we have case studies to showcase later. And so we have Media SDK as well as OpenCL, and we have some case studies that highlight use of those. However, there is documentation available that shows how to use the other techniques to take advantage of multiple devices or those multiple accelerators. So once you figure out the path you want to use to take advantage of Intel Deep Link technology, that's either libraries, where it's done for you somewhat automatically, or direct programming, you also want to understand what development tools you need to use. Well, when developing for Intel Deep Link technology, you can still use standard development tools on your particular operating system. So typically on Windows, that would be Visual Studio. On Linux, that might be GDC. And then you would take versions of the previously mentioned libraries and link them into your application. The slide here illustrates some of the performance analysis tools. So once you have actually implemented your use of Intel Deep Link technology, what are some tools you can use to analyze how the performance is and potentially try to improve it? So the tools are Intel System Analyzer. That's part of the Intel Graphics Performance Analyzer. Enables a timeline view across CPUs and GPUs. That's the bottom left here, where you can see as your application is running, you get a view of different characteristics of the application. Intel vTune Profiler provides hotspots and metrics that understands the CPU and GPU activity. And there are some more recently introduced GPU offload view and GPU specific analysis that has been added to Intel vTune Profiler. The third tool shown here is the CL Intercept tool. And this is a tool that allows you to add extra function calls on all OpenCL calls. So it sort of instruments an OpenCL application where you can intercept calls and add your own sort of monitoring. In this case, it's used to create a function profile of your application. That's what's shown on the bottom right. And then the last tool, which isn't shown, but I mentioned, it's GPU view. It shows overall GPU utilization, things like the hardware queue, what's going on there, and other statistics. So these are the development tools that you would use to do performance analysis when you're taking advantage of Intel Deep Link technology. Now that we've talked about Intel Deep Link technology from a high-level view, as well as the development strategies with respect to tools and libraries, now I want to cover some enabling fundamentals. I started working on Intel Deep Link technology over a year ago, and when I started, I thought I need to actually prove to myself that the technology works and that there is performance that can be gained by employing it. And then also I wanted to understand what are some of the potential issues that could arise so that if I saw it in applications, then I'd understand kind of the basics of what the issue is about. So I developed a set of experiments and tests where I said, hey, I made a hypothesis, I believe X could happen, and then I created a test to test that hypothesis and observe the results on a system with a CPU and multiple GPUs. And then from that I came up with what I call fundamentals for multi-device enabling. And these fundamentals are meant to essentially give you confidence in what the technology is about, what it's doing, and also give you some insight so that when you actually do enable it in your application, if you observe some behavior that doesn't align with maybe the performance you're expecting, then you have some basics where you can analyze it and potentially find some issues. So that's the reason why I came up with these fundamentals, and I want to share with you the fundamentals. The experiment actually did not use a 11th gen core processor. It was actually done with an earlier version of an Intel processor with integrated graphics and a GPU, a discrete GPU. And I thought, well, if it's a fundamental, then the experiments that work there should also apply to a number of systems that have a CPU, integrated GPU, and discrete GPU. And so with that, I want to cover each of these fundamentals and discuss those. So the first fundamental is very basic. It's the fact that the GPU can provide compute performance. And for these experiments, for all of these experiments, I started with a benchmark something that represented the application that I cared about, but wasn't the whole application. It was a benchmark, a small piece of it that I could experiment upon, reproduce situations, test again if I needed to. And for this case, I used something very basic, which is a GEM benchmark. It's a general matrix multiplication. It is part of the sample code that's part of the OpenCL SDK. And what I did was I ran multiple combinations of these to test different hypotheses, and that's true for the 7 fundamentals that I show. So that's why it's important to just talk about it right now. So the first fundamental was GPU can provide compute performance. And what I did was I ran GEM, or multiple combinations of it, on the different accelerators, the CPUs and the GPUs, and then recorded the gigaflops, so that's billions of floating point operations per second. That's one of the metrics from running the benchmark. Typically, higher is better. And then I compared the results. And so as you can see on the first set of experiments, I ran 2 GEMs on 2 CPUs and got 63.77 gigaflops. I then ran 1 GEM on 1 CPU and received 72.45 gigaflops. So just running 1 on the system resulted in a faster rate of execution for that 1 GEM. And running 2, since there's more of a workload on there, the system had to contend with 2 different workloads, then the gigaflops rate was a little bit lower. I then said, well, let me run a GEM on 1 CPU and 1 of the integrated GPU. And with that, I saw a gigaflops rate of 90.09. So the work was being distributed better and taking advantage of the available resources. And then lastly, I said, well, let me try 2 GEMs, one on 1 CPU and one on the discrete GPU. And that resulted in the highest performance of 122.35 gigaflops. And so what that showed me was that the GPU, both the integrated GPU and the discrete GPU, could be used to provide compute performance. And so with that, the call to action is consider the performance opportunity of using the GPU for compute. This is the basic assumption here, is that you can use your GPU for compute performance. Very basic experiment, but necessary, and the rest build upon it. Fundamental 2 is that the CPU handles its own work as well as coordinating the GPU work. So the CPU has other things to do on the system because it is the central processing unit for the system. And so the hypothesis was that, hey, I don't want to overload the CPU with too much work to do because it actually may result in a net slowdown. And so to test that for myself, what I did was, again, I ran 2 GEMs, one on 1 CPU and one on the integrated GPU. And you can see the results I got. So the total gigaflops per second, as well as the additive. So what happened on the CPU with respect to gigaflops per second, and then the integrated GPU. And you can see that those two numbers, the 68.79, 21.3, add up to 90.09. So I ran 2 GEMs, one on 1 CPU and one on 1 integrated GPU. And I decided to give that GEM all available threads of the CPU. So I was running 8 threads at the same time. I then said, well, maybe the CPU has some other system work that it needs to do. And so I used device vision to actually split some of the CPU, and only allowed GEM to take advantage of 6 threads of that CPU. So 2 GEMs are still running. It was using only 6 threads, or invoking 6 threads on the CPU, taking full advantage of the integrated GPU. Total gigaflops actually improved, 90.66. And as you can see, since the CPU is using less threads, performance actually went down compared to the previous slide. So 60.94 compared to 68.79. While the integrated GPU actually improved performance, 29.72 compared to 21.30. So the thought here is that the integrated GPU was getting more attention from the CPU, which has to send it work to do, and so was able to execute at its full rate. And then the last experiment, I said, well, maybe 6 threads is taking away too much work for the CPU, or taking away too much of the capability of CPU. And so I decided to try, well, let's allow the CPU to use 7 threads. And so that's the last line of last row of the table there. And that appeared to provide the best results. So 95 gigaflops and the CPU performance is 65.65, so better than taking advantage of 6 threads, a little slower than 8 threads, while the integrated GPU performance stayed about the same, 29.35, so better than when all 8 threads of the CPU were used. And so the call out here is to find, when you're deciding how to distribute the work between the CPUs and the GPUs, you want to find the right balance of CPU host and device processing. So there's other things the CPU needs to do, and so you don't want to use all of the CPU for compute side processing. Fundamental 3 is performance differs between the CPUs and the GPUs. To test this, I decided to run a number of gems on the CPU, the integrated GPU, and the discrete GPU. And then the metrics I recorded were 1, the actual gigaflops rate, as well as the total time in seconds to finish the benchmark run. And so on the first experiment, I ran 3 gems, 1 on the CPU, 1 on the integrated GPU, and 1 on the discrete GPU. And you can see the timing results in that first row. 57.08 seconds, 58.77 gigaflops, 28.77 gigaflops, and 62.89 gigaflops. And you can see the timing results. What you observe here is that the integrated GPU is the slowest of the bunch, and it takes about 4.37 seconds to complete. And so what this says is that the CPU and the discrete GPU are basically waiting for the integrated GPU. And so the scenario here is, consider the 3 gems as part of an entire workload that needs to complete. And so when you split it, you're actually waiting on the slowest of the bunch, which can be problematic. And so the next experiment said, well, let's run that entire workload. And in fact, let's add even one more to that overall workload. Let's run 4 gems and just take advantage of the CPU and the discrete GPUs. And so here's what you see as a result. The gigaflops rate on both the CPU and the discrete GPU are relatively high. So 64.44, 58.27, 64.44, 62.48. And then the amount of time it took for each of these gems to complete, 2 seconds, 2.15 seconds, 2 seconds, 2 seconds. So overall, it took about 4 seconds for those 4 gems to complete execution. It did not take advantage of the integrated GPU. And then lastly, calling on the fact that it takes about 4 seconds for the integrated GPU to run through that benchmark, we said, well, we can do even more work. Let's run 5 gem. Let's include 5 gem in this workload and run 2 on the CPU, 2 on the discrete GPU, and then run just 1 on the integrated GPU. And you can see the results across that entire run, starting on the 3rd row. And what's important to note is that the integrated graphics, 27.6 gigaflops per second, took about 4.5 seconds to run the entire benchmark. But the point here is that you want to balance the workload spanning the fastest and slowest accelerators. Since these things are executing in parallel, you want to give more work to the accelerator that can handle it, that can get it done quicker, and then give less work to the accelerator that is perhaps slower. In this case, it was the integrated GPU, and in that way, no accelerator is waiting on the other to complete work, and you get the most amount of the work complete. Okay? Fundamental 4, performance differs when running on DC versus AC. And what I mean by DC versus AC is you're plugged into the wall versus running on battery. To test this, I ran 2 gem, 1 on the CPU, 1 on the discrete GPU, when it was plugged in under AC power, and you can see the performance results, 122.51 overall gigaflops, and you can see how they're spread out between the CPU and the discrete GPU. I then ran on battery, 2 gem, 1 on the CPU, 1 on the discrete GPU, and saw that the performance actually was slower, so 102.91 gigaflops, and you can see the separation or the split between CPU and discrete GPU. And what you see here is that under battery, the processor has inherent features that try to conserve power by clocking the frequency down, both the CPU and the discrete GPU. But one observation is that the CPU performance actually dropped lower than the discrete GPU when running under battery. So the CPU under DC, the performance is about 30% lower, while the discrete GPU performance lowered about 10%. And the far right shows a tool called core frequency that goes and actually confirms what the frequency of the CPU was when executing these workloads. So just a screenshot to show you what was going on there. Maybe an interesting tool for you to take advantage of. So the call out here, the fundamental is factor battery life reduction of performance into your workload distribution. So if you're going to run a fair amount of the time under battery, you may have a different partitioning of your algorithm between what runs on the CPU versus the GPUs. Fundamental 5. The GPU may be employed by other client processes at the same time. And so previously I said, hey, the CPU may be being used for other things. Well, the GPU may also be used for other things besides your compute workload. And the obvious one is that, hey, the GPU is displaying the contents of the screen. And so to test the boundaries around this, I decided to run a graphics intensive workload. It's also a CPU intensive, CPU and graphics intensive workload on the system while at the same time running GEM to see what happens. So the graphics intensive workload I chose was a WebGL Aquarium, and it's pictured in the right. The first thing I did was I ran just the WebGL Aquarium by itself and tested or obtained the frames per second, which was 20. So this was sort of the baseline performance. I then ran WebGL Aquarium with one gem on the CPU. So I ran the Aquarium benchmark as well as one gem executing on the CPU. And what I noticed was that the performance, the frames per second of the Aquarium dropped to 12. And then the gem gigaflops performance was 53.14. I then decided to run that one gem on the discrete GPU, which by the way was also coordinating the display on the system. And what I saw here was performance went substantially down for the Aquarium. So it went down to 1 frame per second because much of the discrete GPU was being used to run GEM at the same time, so 61.89. Then lastly, I said, well, let's take advantage of the other GPU on the system, and that's the integrated GPU. So ran WebGL Aquarium. Again, it's running the display and the screen is being controlled by the discrete GPU, whereas the GEM was able to run on the integrated GPU. And in that case, I saw performance of the Aquarium back to the baseline of 20, and then also some decent performance of GEM running on the integrated graphics. And so what we want to call out here is factor other users of GPU into your workload distribution. So if you're using the screen on your system and it's being controlled by one of your GPUs, then you may want to choose a different distribution of your workload so that the display is not penalized by running compute at the same time. Fundamental 6, data transfer times can impact performance. And so what I wanted to see here was the impact of memory transfers between the CPU and, in one particular case, the discrete GPU, because the CPU and the integrated GPU share a common memory. It's the main system memory, whereas the discrete GPU will have its own memory separate, and in terms of executing on the discrete GPU, typically you need to copy memory from the CPU, the system memory, to the discrete GPU. So to test the boundaries around that, what I did was I ran several gems and I modified the size of the matrices of the matrix multiplication. So size 3,968 elements. So that was 3968 by 3968. And I did that one on the CPU, one on the integrated GPU, one on the discrete GPU, and then measured the gigaflops. You see that in the first 3 rows. I then reduced the size of the matrices to 898 and then wanted to see what the performance difference was between the CPU, integrated GPU, and discrete GPU. So when running on the CPU, between the larger size array to the larger size matrix to the smaller size matrix, I saw that running on the CPU increases performance 15% with the smaller size. So the CPU essentially had less work to do, less memory to work or that it had to work on, and so it was able to actually increase the overall gigaflops performance. On the discrete GPU, actually saw performance go down with the smaller size. So that was very interesting. So 25% the performance was reduced with the smaller size, 49.28 compared to 65.22. And what this says with the discrete GPU is that the cost of transferring the memory from the system memory, so what's on the CPU, to the discrete graphics, that transfer time was not amortized by the amount of work that needed to be done. So typically what you want to do is you transfer the memory over to the discrete graphics, and there's enough work there, there's such a large amount of compute work that that transfer time is hidden from the overall processing and can actually end up running faster than the CPU. But in this case, because there just wasn't as much memory to be transferred, there wasn't as much calculation to be done, the cost of those memory transfers between the CPU and the GPU was larger and resulted in a lowering of the performance. And then lastly, we see the workload running on the iGPU. It actually increases performance minimally with the smaller size, and that's because the memory is actually shared between the CPU and the iGPU, so those memory transfers amount to not much. So the fundamental is understand the workload size range and the impact of data transfer time on your discrete GPU performance. So the discrete GPU can have good compute performance, but you need to factor in getting the memory over to the discrete GPU. And is there enough work there that the relative better performance of the discrete GPU will overcome the cost of transferring the memory? And then lastly, another memory-themed fundamental. GPUs have memory limits. And so for this set of experiments, I ran one gem, and I again varied the size of the matrix multiplies from 8064 to 16,256 to test when the program essentially would stop running. And I saw some interesting results. So the CPU was able to perform the matrix multiplication successfully, whereas the integrated GPU was not able to do that at either size. And then the discrete GPU actually had problems with a 16,256 element. And the size of those matrices, the 8064 by 8064 is about 248 megabytes, and then the 16K by 16K is about 1 gigabyte. And your actual discrete card may have more memory than 1 gigabyte, but there are limits in the actual library used. This is OpenCL, and so there may actually be some limits on the largest size of an object that you can allocate on a particular GPU. And so those are somewhat system and runtime dependent. You need to understand that, and that's why they, even though the discrete graphics memory was larger than 1 gigabyte, it failed. And so that's something that you want to understand when you're designing your application and allocating your objects to the integrated GPU as well as the discrete GPU. There may be memory limits that you bump up into. So understanding that will help you decide how to distribute the work and which objects to allocate where. I just ran through the 7 enabling fundamentals. Again, these are somewhat basic ideas, basic concepts that you want to understand before you distribute your application across the accelerators, across the CPUs and GPUs. And so that when you actually do the work on your system, on your application, you can come back and say, hey, I ran into an issue having to do with memory. Could it be that I am not amortizing the cost of the memory transfers? Or hey, I'm actually bumping up into performance issues, and perhaps the slowest accelerator out of the bunch is limiting the performance of the others, and so maybe I need to pursue a different workload distribution strategy. So again, these fundamentals will help you as you develop your deep link based application. And so lastly, I want to talk about 3 case studies that highlight different aspects of enabling Intel Deep Link technology. And the 3 applications, one's Handbrake, and it takes advantage of Media SDK. The second is Blender, it takes advantage of OpenCL. And then the last application is Layla Chess, which also uses OpenCL. The first case study is Handbrake, which is a free and open source tool for converting video from nearly any format to a selection of modern, widely supported codecs. So it's a tool for essentially generating videos. And this particular piece of code is available online so that you can study the implementation. The code itself is pretty compute intensive, so it's taking advantage of the hardware that's available. There's many different algorithms involved with transcoding, batch processing of the particular videos. This particular piece of code has maintained regular updates since it was released in 2003 and currently takes advantage of many Intel technologies, including HEVC encoding. This piece of code was highlighted on the product launch of our 11th gen core processors with Iris Xe and Xe Max graphics. And the bottom right is a chart that showcases the performance. 2 different benchmarks are run. So one was Handbrake doing a multi-encode, so 10 1-minute clips, and then the second was a single encode, 1 10-minute clip. And the performance comparisons were against the NVIDIA MX350 based discrete GPU notebook. And by taking advantage of deep link technology, the encoders and the processing time showed an improvement of 1.78x in the multi-encode case and 2.06x in the single encode case. When you look at the interface for doing the encode, that's what the top left shows. So within the actual queue processing that occurs, you can see that two files are under processing at that particular point in time. And then one of the things you'll want to do when you're confirming that it is taking advantage of the multiple GPUs associated with Intel Deep Link technology is to look at Windows Task Manager, and you can see sure enough that this particular workload was taking advantage of GPU 0 and GPU 1. The way it was done was during the processing, the queue was split across the 2 GPUs. A little more details about the APIs. So it used regular Media SDK API calls for the linkage and for the application. The split between the 2 GPUs is at the application level, so it was above the level of the Media SDK API. Some additional APIs were used, and that's the MFX query adapters number, so that way you actually know how many adapters you have. There may be situations where you only have one GPU, and so you would want to split the work between a GPU that isn't there. And lastly, DirectX 11 implementation is required for this. As I said previously, the implementation is available for investigation, and so you can see the link below to the pertinent source code so you can study for your particular implementation. Next case study is Blender, and it takes advantage of OpenCL to implement the use of Intel Deep Link technology. And what we show here are the changes in the user interface of Blender. If you're unfamiliar with Blender, it's a 3D rendering software, so essentially making 3D highly detailed, ray traced graphic images. And you can see the user interface here. It lists the 2 different GPUs you can take advantage of. And then the bottom right where you are using the particular render engine. And at that point in time is an experimental feature. The middle pane shows the use of the 2 GPUs as the processing occurs. Okay. Performance results of Blender taking advantage of the multi-device rendering, and it shows marked improvement. So Deep Link did 1.5 better performance than using the discrete GPU alone, in this case the Intel Xe Max. and 1.3 better than using the CPU. The CPU is capable of rendering and has been used to do rendering in Blender for a number of years, so it is quite capable. But the combination of Intel Deep Link technology, the combination of taking advantage of the integrated and discrete GPUs, results in higher performance. And so you can see the time in seconds for Intel Deep Link compared to the other processors individually for the classic BMW scene and the classroom scene. API use, so it was regular OpenCL API calls. The split was at the application level, so it's transparent for the OpenCL API, meaning as you move to different platforms, it can take advantage of that implementation on different platforms, and it takes advantage of OpenCL to do that. One of the resource allocation is device specific, so it does take advantage of a OpenCL attribute, in this case CL device maximum alloc size, to understand how much you can allocate on a particular device, and that's something you may have to factor. What the bottom right shows is that there was a difference between what you see in the integrated GPU for being able to allocate an object versus the discrete GPU. And if you recall previous on the fundamentals where there were some limitations with how big the matrix multiply could be between them, this explains part of the situation. For Blender, the implementation is also available online, and you can see the GitHub link in the bottom left. The last case study is Layla Chess, and Layla Chess 0 is a free open source neural network based chess engine. It uses a reinforcement learning algorithm to tune a convolutional neural network. The CNN acts as a position evaluator for the chess program. It is very capable, plays at a grandmaster level in competitions. Also, players use this program to analyze their own games, because Layla Chess 0 actually is said to play more like a human compared to maybe a brute force search engine based chess program. The network has 10, 20, 24, and 30 residual blocks for various hardware. And the challenge is the larger number of blocks that you have, the better the position evaluator is. But the challenge is that the larger the number, it takes more time, more computation to evaluate a position. And so what you want is a balance between the strongest position evaluator you can have versus the number of nodes you can search in a second to help the chess program go as deep as possible in the search tree before recommending a move. The nice thing about Layla Chess 0, it has a number of backends and a scheduler that allows it to send batches to multiple backends. And in this case, we're using multiple OpenCL backends, and you can do it in a multiplex, demultiplex, and round-robin mode. So a good program for evaluating different scheduling algorithms and techniques. And as you can see on the bottom of the screen is a number of performance measurements that were obtained on different size networks. So these are different neural networks, which different size in terms of number of residual blocks and filters. And you can see the performance taking advantage of the discrete GPU and integrated GPU individually, and then combining them together using Intel Deep Link to get a essentially additive performance. And this was done on an early version of Tiger Lake, so essentially a Tiger Lake system put in a desktop configuration chassis, and so the performance is what you get there. One of the things we observed as we evaluated the Layla Chess program on a commercially available laptop, in this case it's a 11th gen Core i7 1165 G7 with the Iris Xe Max graphics. One of the items noted was on this notebook platform, it was a shared 30-watt power budget. And so what happened while we were running the workload is that if you individually ran or took advantage of the GPUs, it executed at max frequency when only one was used. But if you use Intel Deep Link together, we noticed that the frequencies of the two GPUs fluctuated throughout the run. And one of the things that highlighted this, or you're able to use to showcase or find it, was the system analyzer. And so as you can see in the graph below, the GPU frequencies of GPU 0 and GPU 1 shows a fluctuation as the program is running. If you run it, again, if you run it individually, then the frequency stays at the top, at the high point throughout the run. And this resulted in not additive, the performance was not additive when you ran the network on discrete GPU and then integrated GPU, and you see the deep link performance as 6002 instead of the more 2 times performance that we saw on the previous platform. Again, this is because the actual notebook has a shared power budget between the different processing elements, and that essentially limited the processors from running at full frequency range for the entire time period. And so that's something to watch out for when you're taking advantage of Intel Deep Link technology on notebook processors, is that there may be power limits that prevent you from getting peak CPU and peak performance if you're trying to use all processing units together. All right, that was the 3 case studies, and they show different aspects of using Intel Deep Link technology. Fortunately, there isn't time to go into the deep details of the implementation and how to do everything associated with those case studies. We just wanted to give you a flavor of taking advantage of Intel Deep Link technology and those case studies, some things you might see as you implement it for yourself. And so in summary, Intel Deep Link technology is the intelligent harnessing of Intel CPUs and GPUs to improve the performance of content creation, gaming, and productivity applications. We discussed the process tools and fundamentals for effective enabling, and then provided some case studies that highlighted methods of employing Intel Deep Link technology. And so my call to action for you today is to consider leveraging Intel Deep Link technology to improve your application performance. Thank you for attending today's talk. There are other talks here at GDC that have Deep Link technology. The 3 are listed below, as well as a white paper that will be released that speaks to some of the stuff I shared in more detail and has other pieces of the puzzle of using Intel Deep Link technology. Well, thank you and have a nice day.